Okay, let's start. The second talk is given by Professor Kai Brandner from Nottingham. He will tell us about thermodynamic uncertainty relation for coherent transport. Let's start.
Okay, thank you, KG, and hello, everybody. So let me first thank the organizers of this very nice meeting for giving me a chance to give this talk. And I will talk about work that has evolved over a couple of years. And particularly most of the results that I'm going to present will be drawn from these two papers here. The earlier one with Taro Hanasato, who used to be a student of Keiichi Saito at Keio University, and the later one together with Elina Potanina, who used to be a student of Christian Flint at Aalto University, and Michel Moskalets, who used to be a visitor there at the time when this work was done. Okay, so I would like to talk about coherent transport, and before we come to that, perhaps as a little introduction, let us think about transport in macroscopic systems again. So here we have a macroscopic conductor, which in practice may look something like in this picture here. And the usual situation is that the dimension of this sample is much larger than the mean free path of carriers that carry current through this conductor. So what does that mean? In a very naive picture, we can imagine transport in these systems taking place through particles that are injected into the sample from some reservoir and then follow some stochastic trajectories, which is characterized by frequent collisions of these particles or transport carriers, either with the bulk material or with other carriers. And now this process naturally admits a characteristic length scale, which is the mean free path between two such collisions. And as I said, typically macroscopic systems, this mean free path is very small compared to the size of the sample, which then gives rise to diffusive transport in generic situations. And now we can imagine that we make the sample smaller and smaller, and at the same time reduce the temperature, which will increase the mean free path of carriers between consecutive collisions. And if we do that, at some point we will reach a regime where this mean free path becomes comparable to the size of the sample, and that's exactly the situation that we refer to as coherent transport. So typically that happens at very low temperatures, which means that quantum effects play an important role. So we do not have classical trajectories anymore. Instead, we have to consider propagation of wave packages through these samples. And as I said before, if the mean free path is sufficiently large, then this will be a phase coherent propagation, and hence the name of this transport regime. Also, and that is what will become very important in following, these systems are usually well described in terms of non-interacting carriers. So we don't really have to talk about interactions between these carriers inside the sample, which would make things very complicated. Now, obvious question is probably, I mean, can such systems actually be realized? And the answer is yes, of course. For instance, in atomic junctions, in semiconductor structures, or nowadays also with cold atoms, where this kind of reservoir and conductor structure is realized with optical traps. So these are just a few examples, and in my opinion, at least, these systems are a very useful platform to do quantum thermodynamics. First, because they can be realized in experiments and controlled with a very high degree of accuracy. And second, these systems admit a very transparent and simple theoretical description, which gives us access to analytical expressions in situations where more complicated systems, such analytical expressions, would not be available. Okay, and today I want to use this platform to discuss a particular topic, namely thermodynamic uncertainty relations. And I really don't think I have to say much about that anymore, but just for the sake of completeness and perhaps as a little reminder of how it all began. So thermodynamic uncertainty relations were first discovered for steady-state time homogeneous Markov jump processes that live on some network of discrete states, which could look like that or have any arbitrary structure, transition rates between these states. And the quantities that we are interested in are the mean current across a particular link in this network, the fluctuations of this current, and the total rate of entropy production that is incurred by driving the system away from equilibrium, so that there is a finite mean current. Now, in terms of the microscopic structure of these Markov jump networks, these quantities can be defined here in this way. So just the usual expressions. And we assume that these rates satisfy the balance conditions so that the entropy production in the environment during a transition through a particular link xy can be represented in this way. And if all these conditions are met in the steady state, we have this quite remarkable simple relation here, which gives us an inequality connecting entropy production, current fluctuations, and mean current. So that was this state of the art 7 years ago, and since then there has been an enormous amount of research, a lot of which we have seen during the last days, and it's really impossible to summarize all of that here. I basically just move on, and the question that I would like to ask is, can we derive such thermodynamic uncertainty relations for coherent transport systems? So to make this question a little bit more precise, we have to discuss how we actually describe coherent transport. And here we use the standard Landauer-Büttiger model, which works as follows. So we assume that our sample is some arbitrary scattering region, which may feature some arbitrary scattering potential, and may also be subject to some external magnetic field B. And this scattering region is now connected to a set of reservoirs, can be arbitrary many, via perfect semi-infinite leads. And then we assume that these reservoirs inject non-interacting transport carriers into the system, which then propagate through the leads, through the scattering region, and then out through the leads again until they are absorbed reflectionless into the reservoirs. Reservoirs are, of course, in thermal equilibrium, so they are characterized by temperature and the chemical potential. And in this setting, you can now write down formal expressions for the mean electric and heat currents in terms of these operators. Yes, because we're doing quantum mechanics, these observables are represented by some operators in the Heisenberg picture. And these angular brackets here denote the ensemble average with respect to the steady state of the system. Okay, so we have mean currents and we have fluctuations. And now, because we assume the system is in the steady state, there is no net entropy production taking place inside the sample. So the entire rate of entropy production really is incurred in the reservoirs and therefore can be written in this standard form here, where Q is the heat current flowing out of the reservoir alpha and T is the corresponding temperature. So now we have all the quantities defined that go into the original thermodynamic uncertainty relation. We can ask if there is a universal relation between them. In particular, we can also ask what is the role of quantum effects. And to address this question, it is useful for a minute to go back to a classical picture. Now, let's assume for a minute that there is no quantum mechanics and our transport carriers are just classical particles which are injected somehow by this reservoir and then follow a classical trajectory which can look very weird inside the scattering region due to some scattering potential. And then they go again into the lead until they are absorbed again into the reservoir. Now, because this is now a classical setting, we have to replace our current operators with phase space observables, where psi here is the phase space trajectory of the entire system. Okay, now if we make these assumptions, then we can basically use the formulas from the previous slide mechanically and calculate the mean currents and the current fluctuations, and they assume this very simple form here. This form is, of course, so simple because we assume that the carriers are not interacting. What goes into these equations are, unsurprisingly, the usual Maxwell-Boltzmann distributions, which characterize the reservoirs, and these transmission coefficients here, which characterize the scattering region. And in general, they can have a very complicated form, but it will not really matter in the end what these coefficients are. The important bit is they are positive. They satisfy the sum rule here, which is a result of Liouville's theorem, and they obey this relation here, which is a consequence of time reversal symmetry. Okay, now with this setup, it is relatively easy, at least in hindsight, to show that there is a thermodynamic uncertainty relation. And if there is no magnetic field, we recover exactly the classical version of the thermodynamic uncertainty relation, which is not a big surprise, because if there is no magnetic field, then this entire transport process can be mapped on a biased random walk. If we turn on the magnetic field, then the symmetry between these transmission coefficients is broken, and that forces the factor on the right-hand side of the thermodynamic uncertainty relation to go down to this irrational value, which is roughly 0.89, and it can be found by explicit minimization. I should also say that this bound can be asymptotically saturated in cases where you have many terminals and strong magnetic fields. So this in general is really the best bound you can get. Okay, so much for the classical side. Now let's go back to the quantum case. And now again, we have to give up on the notion of classical trajectories. Instead, the particles that are injected by the reservoirs are now plane waves or beams of plane waves that propagate coherently through these leads. And then there's some, in general, complicated interference pattern inside the scattering region before this beam is split into a coherent superpositions of outgoing beams propagating back into the reservoirs. Yeah, and each such process is described by a particular state in this in the single particle Hilbert space, which is a scattering state. So the spectrum of this Hamiltonian will be continuous because these leads are assumed to be infinite. Okay, and now with this setting, again, quite mechanically, one can now calculate explicit expressions for mean currents and noise. And what you see is the expressions for the mean currents are essentially the same as in the classical case, with the only exception that the Maxwell-Boltzmann distribution now has to be replaced with a quantum distribution, which here is a Fermi-Dirac distribution because I consider fermionic carriers. I should also say that in these equations here, I assume that the leads are effectively 1D, which is usually a good assumption because one can make them very narrow. That is basically just for the sake of convenience to keep these formulas tractable. Okay, for the current fluctuation situation is a little bit more complicated. So these fluctuations naturally decay into two contributions. The first one is the thermal noise, or the usual Nyquist-Johnson noise, which persists in equilibrium but vanishes at zero temperature. The second contribution is the shot noise, which stems from quantum fluctuation. And these quantum fluctuations occur precisely because any incoming beam of carriers can be split into a coherent superposition of outgoing beams. So that's what is described by the shot noise. This quantity is zero in equilibrium and persists at zero temperature. Okay, and now we have these transmission coefficients. Again, these are positive quantities which depend on the scattering matrix describing this process and can be very complicated, but we are not particularly interested in their detailed structure. The important bit is we again have the sum rule here, which follows from unitarity of Schrödinger time evolution, really. And we have this relation here following from time reversal symmetry. Okay, now with all these expressions in place, we can go and test the thermodynamic uncertainty relation in this coherent conductor setting. So let's consider a, let's consider a relatively simple model for a coherent conductor. So what we have here is a sample consisting of a chain of quantum dots, and you may think of these quantum dots as cavities in some 1D conductor that are created, for instance, through quantum point contacts. So everything inside this sample here is still coherent. This is not a Markov jump process. Now each of these dots is characterized by some on-site energy, and then you have some tunnel coupling between these dots, tau, and they can be different. And we apply a symmetric bias, and we assume for simplicity that the temperatures of the reservoirs are equal. Now what we do is we fix the number of dots, and then we minimize we try and find the optimal parameter configuration such that the uncertainty product, which is this coefficient here, which in a classical case would be bounded by two from below, so that this coefficient becomes minimal. And if we do that, we find that for a single dot, the classical uncertainty relation, with this bound is indicated here by the shaded area, is still obeyed. If we have two dots, then we observe some slight violations, which can become stronger and stronger the more dots we allow. And if we take the limit n to infinity, this coefficient can really be arbitrarily small. should say that these results were obtained early in several papers, two of which are cited here. Now, how can we understand that? And to this end, it is useful to have a look at the transmission function that actually describes these optimal quantum dot chains. And what we see here on the right-hand side is this transmission function as a function of energy. And for a single dot, we just have this characteristic Lorentzian shape. And as we increase the number of dots, this shape becomes more and more narrow and asymptotically approaches this boxcar type function. And what this boxcar type function does is it effectively cuts out a section of the Fermi distribution. And that's what I try to indicate here in this sketch. And what this is supposed to show is that the scattering states that are originating from the left reservoir are essentially fully occupied if we apply a sufficiently large bias, while the scattering states originating from the right reservoir are essentially empty. And this effect basically kills all thermal fluctuations. At the same time, this boxcar function is deterministic in the sense that the transmission coefficient, which can be regarded also as a transmission probability, is either 0 or 1. And therefore, the shot noise is also 0. So in these systems, the noise can really become arbitrarily small if you make the bias large. And that's, in the end, really a result of the structure of the Fermi distribution function. Okay, so now we may ask, actually, can we do something about it? And can we take this effect into account? And the answer is yes. And to this end, it is useful to have a look again at the anatomy of the current fluctuations. As I said before, as a thermal and the shot noise contribution. And now we can again further decompose the thermal contribution into a quasi-classical one and an exchange correction. So this quasi-classical noise is given by this expression here. It's a positive quantity. The exchange correction has this structure. Here is also a positive quantity. So this is the object that reduces the thermal noise, and that's exactly, I mean, it encapsulates exactly the effect that I tried to describe on the previous slide. And then you have the usual shot noise, which is also a positive quantity. And now what we can do is we can bound this we can show that this classical noise contribution obeys the conventional thermodynamic uncertainty relation. And that means because the shot noise is positive, we can throw it away, and we end up with a relation of this type here, which now contains the ordinary current fluctuations and this exchange correction, which is in itself not really a measurable quantity. And therefore we have to, therefore it's natural to ask the question if we can bound it in terms of something that can actually be related to physical quantities or physically accessible quantities. And the answer is yes, you can bound this exchange correction in terms of the total entropy production so that you have this expression here. And now if you just put all of these bounds together, you end up with this thermodynamic uncertainty relation for coherent transport, which has this form. And that's really the main result that I wanted to show you. On the right-hand side, again, you have this factor psi, which is 2 if there's no magnetic field, and roughly 0.89 if there is a magnetic field. This bound is, of course, weaker than the classical thermodynamic uncertainty relation. You can rewrite it in terms of bound of entropy production, which then takes this form here in terms of these rescaled Fermi factors. Yeah? So E here is just the carrier charge. Okay, now we may ask, how good is this bound? And if you now plot this bound for our quantum dot chain, you get this picture here on the right-hand side. The shaded area is the bound that we have just derived, and we see that this bound is saturated for very small biases. But then this coefficient here, which is the analog of the classical uncertainty coefficient, really grows rapidly as we increase the bias. Note that this is on a log scale. So the bound is obeyed. It is saturated for very small biases, but for large biases, there are strong deviations between the actual coefficient and the bound that we have. So that's what but the important bit is, yeah, I mean, that we have a relation that is only involving physically accessible quantities, and the entropy production, the noise, and the mean current. So this bound, although it looks, at least for this system, as if it would not be particularly good, lives on the same parameters as the classical thermodynamic uncertainty relation. Okay, just a few words to wrap this up, perhaps about generalizations. You may now ask, what happens if you introduce some dephasing into the system or some inelastic scattering. If you want to do that on a microscopic level, things become extremely complicated, but there is a heuristic way of including such effects, so-called probe terminals. So what we can do is we can just pick one or an arbitrary number of these terminals and adjust the chemical potential and the temperature in such a way that the mean currents flowing out of this reservoir are zero. And in this case, these terminals do not contribute to the net transport process, but you can still have carriers that go into this terminal, are then thermalized and are injected again into the system. So you introduce some degree of dephasing or inelastic interactions on this heuristic level, which is, however, frequently used and has proven to be a quite powerful tool in mesoscopic physics. Now, because the original relation that I derived did not really hinge on the values of these temperatures or these biases, then of course you have still the same thermodynamic uncertainty relation as before. Another interesting generalization is if you apply periodic driving. So we may imagine a situation where the scattering region is also subject to some oscillating electric or magnetic field, in which case the energy of the carriers can change as they transverse this scattering region. And this periodic driving gives rise to another contribution to the current fluctuations, which in itself is again not really a measurable quantity, but it can be bounded in terms of the temperatures of the reservoirs, and then you end up with this slightly more complicated relation. Again, it has the advantage it lives only on the original parameters of the thermodynamic uncertainty relation and some fundamental constants here and the temperature of the reservoirs. So it is an operationally accessible bound. Okay, perhaps just a few words about applications. Now, once you have a non-trivial bound on entropy production or some form of thermodynamic uncertainty relation, you can, of course, derive bounds on the efficiencies of all sorts of devices, as was pointed out first in this paper here.
Okay.
And for instance, we assume...
Now you are entering the question time.
1.5 minutes, I'm almost done.
Yeah.
So for instance, we may assume that we have a situation where one of the reservoirs is hot compared to the other, and we apply a thermal bias, a chemical bias against the temperature gradient, and then we can use the temperature bias to drive a particle current uphill, in which case we have constructed a thermoelectric heat engine. Now we can use the bound that I have just shown you to derive a bound on the efficiency of such devices in terms of these factors F here, which are really the ratio of the fluctuations of the output power and the mean value of the output power. And this thing here tells you that you have Carnot efficiency, eta C, only if the F diverges, and that happens either if the output power is zero or if the fluctuations of the output power diverge. So qualitatively, this result has the same implications as its classical version, which has been derived in this paper here. Now, as a second example, I mean, just to show what we can actually do with these bounds, you might apply this to quantum motors. So that's an idea that was put forward here in this paper by von Oppen and co-workers. So we assume we have some coherent conductor, and this coherent conductor is somehow coupled to a mechanical degree of freedom. For instance, you may imagine this to be a little cogwheel with charges on its surface. And then as these charges pass by the conductor, they create sliding potential walls inside the conductor. And that's an effect that you can describe as a periodic field. And therefore, we can use our thermodynamic uncertainty relation for periodically driven coherent conductors to construct a bound on the efficiency of such devices, which is now given by the ratio of the mechanical output power that goes into this little wheel and the electric power that you have to put in to drive the wheel. So it's like an electric motor, if you wish. And again, this bound is by the second law, this quantity is bounded by 1. And with our relation, you obtain the stronger bound here with these generalized Fano factors given down here, essentially the same structure as before. You have current fluctuations and you have, you have power fluctuations. Now this is the input power here and the mean input power. And what you see is that this quantity can become only one, either if the mean input is 0, in which case the mean output would also be 0, or if the fluctuations of this electric power diverge. Okay, so that's basically what I wanted to say, just briefly to wrap this up. So I hope I could convince you that coherent conductors are useful systems to do quantum thermodynamics and to explore the role of quantum effects for thermodynamic relations. We have derived these two relations here. This is really the main output of this research. And there are open problems, of course. Yeah, I mean, one question is, of course, saturation. I am not aware of any situation beyond linear response where this bound can be saturated. And I don't think they can be saturated beyond linear response, but I have no hard results to underpin that. Second question would concern fluctuations of the heat current, which could nowadays also be measured. These same bounds cannot apply to heat current simply for dimensional reasons, yeah, because the dimension inside this bracket here, the dimensions of the fluctuations and the entropy production would not match. Bosonic carriers are another question. It has been shown some time ago that the classical uncertainty relation holds if you have bosonic carriers, but it may actually be possible to derive a stronger bound than the classical relation, because the bosonic character of carriers gives rise to enhanced fluctuations quite in a similar way as the fermionic character suppresses fluctuations. And finally, the ultimate goal of these efforts would, of course, be to have a unifying framework covering all of these bounds, including those that are not yet established. So for instance, yeah, if you look at this bound down here for periodic driving, if you turn off the driving field, that does not reduce to the bound above. Also, it is unclear at this point, at least to me, how this bound would reduce to the conventional uncertainty relation in some classical limit. And so all of these questions are still open. Thank you very much. I am done at this point.